Hello and welcome to the session on NVMe and computational storage. I am Kim Malone and I work on computational storage for Intel and am co-chair of the NVMe Computational Storage Task Group.
Hi everyone, my name is Stephen Bates. I'm the Chief Technology Officer at Adedicom. And with Kim, I am another one of the co-chairs of the task group on NVMe Computational Storage.
So today we're going to be talking about a couple of things related to NVMe computational storage. First, we're going to talk about motivation and background, why NVMe, the architecture for NVMe computational storage. We'll go through some example flows. We'll talk about the changes to NVMe for computational storage, and then we'll put out a little pitch for NVMe computational storage task group.
So motivation, why computational storage? I think it's very clear to everybody who attends SDC that there has been an explosion in stored data in recent years, and we certainly don't expect that to change anytime soon. At the same time, there's also been a shift in the power or potential of some of the different things that make up computer architecture. So for example, CPU capabilities performance is stagnating, maybe growing slightly slower, whereas things like SSD bandwidth and latency are rapidly improving. And that's creating disruption in computer architecture that things like NVMe computational storage are trying to take advantage of. For example, we've seen a move away from the central processing unit towards a more heterogeneous data center with things like graphic cards being used to augment compute, artificial intelligence inference engines, smart NICs and DPUs, etc. And also a move towards a more distributed processing model where applications scale out across many, many servers and are connected together with some kind of networking fabric. There is a desire to run our data centers much more cost effectively. And one of the ways to achieve that is to reduce the amount of data movement, something that computational storage, and in particular NVMe computational storage, tries to solve. If we can achieve this reduction in data movement, we can save power, which reduces the TCO of our data centers, which is very, very important. We actually free up networking bandwidth, and networking bandwidth is a huge challenge for large-scale data centers right now. And we free up host CPU cycles so they can focus on the tasks which are more value generating. So using your central processing unit for the things that it's best suited for in order to maximize customer experience and profits for data center operators. The other thing I will say is there is a motivation for standardizing interfaces for the offloading of compute near storage. So right now, as I mentioned, there's a lot of different heterogeneous compute models and different vendors providing different solutions in the marketplace. But everyone has their own software and programming interface. And what we're seeing from the end consumers of these accelerators is a desire for standardization. And NVMe computational storage plans to achieve that. So if we move forward to the next slide, I'm going to talk a little bit about background. So if we jump into the background, we can talk about what problem are we solving? Well, as many of you know, not only has the amount of data increased exponentially over the last few years, but the complexity of that data has also increased. So we're storing data in more complex formats. We're storing a much more heterogeneous mix of structured and unstructured data. And these massive, massive data warehouses are becoming much more rich in terms of the data that they have, how the schema that we use to describe them. And we're storing data in really what is a mismatch of these arbitrary data formats. So we have JSON and XML and CSV and Parquet. And we're really, as an industry trying to work out how to standardize, how to lay that information down on block storage media and how to access it. On top of that, for reasons of security and cost optimization, we're seeing a lot more data get encrypted and compressed, either as it moves onto the drive through drive level encryption and compression, or even before it gets to the drive. And that can consume a lot of CPU cycles, and data center operators don't like paying for that. On top of that, the formats and the data are constantly evolving. So even if we try to standardize on some kind of formats today, they may not necessarily be the popular formats of tomorrow. So we need something very flexible. As an example, we can consider some kind of database where we've laid down a reasonably rich schema onto the disk. So we may have these combinations of metadata and data that form some kind of tuple set. We may have some kind of header and footer that may be there for data integrity and also for record keeping. And these records, right, which may belong to a database or a big analytics stack like Spark or Hadoop, they could be compressed or encrypted and stored in some kind of arbitrary format. And what we're moving towards trying to standardize with NVMe Computational Storage is how do we get a scheme whereby data that exists on disks that are computationally storage aware can be asked by the host to perform operations on that data without moving that data back to the host. So how can we do in situ processing, computational storage? And a very simple example of that is how could I ask a drive full of data with schema around people's names and where they live and perhaps what their telephone numbers are and their addresses and what were their last recent purchases on something like Amazon? How could I possibly ask a drive that holds a lot of that data a question that might be sensible to ask, like how many of these people live in New York? And so this very simple example shows how we might do that. We may decrypt the names. We may decompress those names to get them into a format we can understand. We then may run a filter where we look for the state in which where those names reside. And then we may count up how many occurrences of a filter match we get. So in this particular example, we've asked the drive to tell us how many people from our database live in the state of New York. And the answer we get is 3. And we and the people participating in this standardization effort really feel like standardizing the ability for an NVMe controller to do this type of thing has a lot of benefit for the industry and a lot of benefit for the end consumers, and is something that vendors of NVMe products should be able to provide. So if we move on to the next slide, we have to ask the question, why NVMe? Or if you're me, you have to ask the question, why not NVMe? So when a group of storage architects from a range of different companies came together a couple of years ago to talk about computational storage, it was very clear right from the start that NVMe was a very, very viable candidate for the protocol over which we should focus the standardization. It's been a very successful protocol to date. The number of NVMe units shipping today is absolutely massive. The amount of data stored on NVMe drives today is absolutely massive, and it's expected to grow at a very significant growth rate for the next 5 or 6 years, and probably even longer than that. The NVMe protocol is very efficient. It's very well supported. It has a very rich ecosystem. One of the things we need to consider is if we're going to deploy these types of devices in a data center, we're probably going to deploy them at quite large scale. And there are people today who are deploying literally millions of NVMe devices in their data centers around the world. So NVMe has already demonstrated that it can scale to the kind of scalability that we need for computational storage. We have a very active community working around NVMe. Many large companies are doing work on NVMe products, and many of their software teams and many other companies that are software centric are working on software around NVMe. It's a very extensible and efficient protocol. It's a very soft touch on the processing unit. The driver model is very efficient. It was designed that way. And it's well suited to today's modern server CPUs that tend to consist of many cores, not necessarily running at the highest frequencies. One of the great things about NVMe is it has support across multiple transports. PCIe devices are obviously a very familiar class of NVMe devices, but we also have NVMe over fabrics, and it's very likely that NVMe will move to other protocols in the future. NVMe already comprehends storage and data very well. It understands things like encryption. It has security models. It has the ability not just to work with LBAs, but thanks to recent additions to the standard, we can also work with zoned devices and also key value. So the question really becomes, why not NVMe? If we move to the next slide. I'll hand over to Kim, who's going to talk more about the computational storage architecture.
Thanks, Stephen. Just a super high level overview of the architecture we're talking about. There's a couple of key things that are involved in the architecture. It's a memory-centric architecture. We have compute engines to do the compute on the NVMe controller. We have eBPF as a program type that we're supporting. And we have a concept of programs, which can be either downloadable or device-defined programs. And just as a point of order, all of the NVMe content that we are describing today, we're describing NVMe work in progress, which is subject to change without notice. The content here are contained within technical proposals, which are being developed right now. And once they become part of once the proposals are finished and they become part of the standard, then they're no longer subject to change. But right now, they're very much under development. So the major components that we have in this architecture are shown in the picture here. So one of the main concepts is that programs operate only on data that is in controller memory. They don't operate directly on namespaces. And this includes both program input and output. And the data is moved between controller memory and host memory using new NVMe commands, and is moved between namespaces and controller memory using existing IO command set commands. And one of the advantages of that is that no matter what type of namespace and what type of IO command set is associated with that namespace, you can still use that with computational storage to move things into and out of controller memory. So that means you can use a block IO namespace or a key value one or a zone namespace. Some of the other things you see on the picture here are compute engines and programs. And we will talk about those in a little more detail in a minute. The other thing to note here is that these concepts are contained within an NVMe controller. So the main unit of offload in the NVMe Computational Storage architecture is a program. So these programs are invoked and used in a standard way. They're conceptually similar to software functions in that they're called with parameters. They run to completion. As I had said before, they operate on data in on-device memory, which we're calling controller memory. The programs run on a compute engine. The programs may be in hardware or software. So a device may offer fixed function programs that could be something implemented in an FPGA or in an ASIC. And then in addition, we are supporting programs that are downloadable in eBPF, which is a hardware agnostic bytecode from the host, and then can be later executed. And as I mentioned before, programs are managed on a per NVMe controller basis. So as I mentioned a minute ago, compute engines are an element of this architecture. And a compute engine, as we're defining it here, is an entity on a controller that can execute a computational program. So that could be a core, CPU core, or as I said before, an ASIC or an FPGA. Within this architecture, compute engines may have asymmetric access to controller memory. So there might be some memory that is, as shown on the diagram here, that could be embedded within a compute engine. Let's say, for example, an FPGA that has onboard memory, or it could be memory that's shared across other compute engines. And along those lines, a computational program may only be able to execute on a subset of the controller's compute engine. So let's say we have, let's say an ARM compute and we have an FPGA. So some of the programs can run on the ARM, but may not be able to run on the FPGA and vice versa.
So I'm going to pick up from Kim and talk about the last two major components of the architecture that we're discussing today. So the first of those is, thank you, Kim, downloadable and device-defined programs. So these are two different categories of programs that can be executed on an NVMe controller. So in the initial architecture model, the plan is to support both device-defined and downloadable programs. As you might expect, device-defined programs are fixed programs that provide some kind of consistent, fixed functionality. Examples of that could be compression or decryption, and those are provided by the NVMe controller. The functionality implemented by the device that is callable as a program, right? So these can still be run as a program, but now it's a fixed program that doesn't change over time. And these are going to be very, useful in NVMe controllers for these kind of functions that we've talked about, and also other functions that will be developed over the time. The other type of program is the downloadable program, and these are programs that are in some kind of descriptive format that can be stored as a binary on the host and then pushed down to the device via NVMe commands. So these are programs that can be loaded onto the NVMe controller and then run on the controller. And, for example, this could be an FPGA bit stream, or it could be some kind of compute instruction set architecture. So think machine code, or even a higher level language, though there isn't any current proposition to standardize a high level language. Now, that being said, there is a plan to standardize around one specific instruction set architecture, and that is something called eBPF. So eBPF stands for Extended Berkeley Packet Filter. For those of you who are not aware of it, it's quite a successful vendor neutral virtual machine definition that includes an instruction set architecture. So you can think of it as essentially a CPU, or the definition of a CPU that is vendor neutral. So many people can implement it, or you can use what's called a just-in-time compiler to take eBPF code and map it to machine code that runs on a different architecture, for example, ARM or AMD 64, or even something like RISC-V. So the question is, why do we need these types of programs? And then the other question is, why use eBPF? And I'll talk through both of those in the next couple of minutes. By the way, on the right-hand side of this slide is a diagram of the existing eBPF stack that is being maintained by the new eBPF group that is now part of the Linux Foundation. There's a lot of traction around eBPF. It's very well known in the Linux kernel community, but it's also starting to see traction in other places as well. And it's becoming quite a popular way of standardizing how pieces of work get described at a level that's lower than a high-level language like C or Rust, but it's higher than a vendor-specific machine code, like machine code to run on a Intel Xeon or an AMD or some other type of processor. So why do we need downloadable programs? Well, the first reason is flexibility. Obviously, we can't build an NVMe controller that does absolutely everything in fixed function programs. We don't even know what kind of functionality people might want in the future, right? Applications are consistently and constantly evolving, and we don't always know what the best accelerators are. It obviously takes time to put an accelerator into an NVMe controller, and that time can be on the order of years. So we can't really see the future. And so we have to accept the fact that certain engines will have to be flexible. That will tend to be the ones at the cutting edge, and also ones that maybe aren't necessarily needed all the time. We want to be able to process quite complex and changing data formats, kind of back to the example that I showed earlier in the presentation. And in order to do that, we need flexible languages. I've talked already about emerging applications, and we also want to have portability. One of the interesting things about eBPF is it is supported as a target in LLVM, which is a very well-known compiler toolchain. So you can actually write code in a high-level language like C or Rust or a few others, and you can compile that code using standard tools to eBPF machine code, and then push that across the NVMe connection down to the controller. Now the question is, why eBPF? Why didn't we choose something like ARM64 or AMD64 or RISC-V? And the answer obviously is we needed something that's vendor agnostic. NVMe has many companies as members, and those companies use different types of processors in their products. And we wanted to choose a downloadable program format that didn't subscribe to any one particular type of CPU or any one particular type of vendor-specific ISA. So eBPF was a very good candidate for that. We wanted something that was well understood. The definition of eBPF is quite straightforward. You can go look it up, and you can very quickly get a sense of how it works at a machine code level. We wanted something with an existing ecosystem, which eBPF has. We wanted something that had toolchain support, something that standard compilers could use, something that was integrated into something like LLVM. We did want these toolchains to exist, and we wanted something that had a respectable body behind it, and the Linux Foundation meets that goal. So we wanted to have something that wasn't even necessarily something that NVMe had to invent from scratch. We wanted something that was already in existence and was well supported from a kind of management leadership point of view. So eBPF ticks all those boxes. Will it be the last one that we standardize in NVMe Computational Storage? Probably not, but it's going to be one of the first for sure. If we can go to the next slide. Thank you, Kim. So I'll hand back over to Kim to talk through some example flows.
We're going to show, I have a couple of example flows here, but we'll concentrate on one of them in particular. And these are, as the term example flow implies, they're an example of a case of something that you can do with this architecture. It is not intended to be a list of all things that can possibly be done. So this particular example is an example of a simple data filter and shows reading from a namespace into controller memory, executing the program, and then reading it back to the host. So we have another example that adds on top of that and does an additional operation on the data. So this is the one I'm going to go through in detail. So what we're doing in this flow is reading encrypted data from a namespace into controller memory. And that is done using the existing NVMe read command. And you can see that as step A. So the read command gets sent down to the controller. The data is copied from the namespace into controller memory, and then the successful response goes back to the host. The next thing we're doing is executing a filtering, or I should say, we're executing a decryption program on the data. So as you can see, the data is encrypted. So before we can do any kind of filtering on it, we have to decrypt it. So we send an execute program command that says execute the decrypt program on the input in controller memory and put the output into this other place in controller memory. And you can see that our table with some superheroes has reappeared, and now it is decrypted. So now that we have that decrypted data in controller memory, the next thing we do is we execute a different program against that data that does the filtering. So we run filtering program in Compute Engine 0 with the decrypted data that was output from the other program as the input to the filtering program, and the output is just the rows that have a state that is equal to New York. Now that filtering output is in controller memory, and as a final step, in step D, the host issues an NVMe command to read just the result back to the host. So the advantage here is that all of this data didn't have to be pulled up to the host and have the host operate on it there. We can do a data reductive case here and only pull back the end result. The next thing I want to share is the NVMe changes for computational storage. And these changes are optional. So this is not something that, the support for this is not required. It is an optional set of functionality. So there are two technical proposals right now that are for computational storage. The first one is TP4091. And that is the computational program's I/O command set. And mostly that is what we've been describing earlier in this presentation. So the commands that exist there, there's an execute program command, a load program command that is used to download programs from the host. And then there's an activate program that reserves compute engine resources for that program. The other technical proposal is called controller local memory. And this is a relatively new proposal that has been split out of TP4091 to introduce the controller local memory. In addition to these things, we have identify controller command updates that indicate whether this new command set is supported or not. We have new blog pages to support computational programs and to be able to query information about programs and compute engines and things like that. And as I said before, all of this functionality is optional.
So we're going to finish up here, and I'm going to do a brief plug to persuade you all to come join us. This standard is very much under active development. We are looking for input from all different types of people working in the storage sector, on the hardware, on the software, on the ecosystem. If you are interested in getting involved, you can come talk to one of the task group co-chairs, myself, Kim, the other co-chair being Bill Martin from Samsung. The goals of the task group are to define the architecture of TP4091 and take TP4091 through to what we call ratification, which is where it gets integrated into the existing standard. And then obviously to identify other potential TPs that are related or come out of this work. So that's work that's ongoing. We have quite an active community. We have 167 members as of the time we put this slide together from 43 companies, and that'll probably continue to grow. And there are some URLs that you can click on if you want to get involved. For some of these, for these, you have to be a member of NVMe. If your company isn't a member of NVMe, I have to ask why not. So come join us. And for those of you who are super keen to get going as quickly as possible, the group meetings are held between 9 o'clock and 10 o'clock a.m. on Pacific on Thursdays. So if we just jump to the last slide, we'll take a moment to rate the session. But for me, and I'll let Kim say goodbye as well, I want to thank everybody. I'd also like briefly to thank everybody involved in the task group. It's been a very exciting piece of work so far, and I think it has a lot of potential for the industry. So if you aren't already involved, I hope you can get involved. And if you are, thank you for being involved. And thanks very much for your time.
And I'd also echo what Stephen has said. This is this that we're presenting is the result of a lot of people's work, and we definitely appreciate that. And anyone else who's interested in coming out to help us out, please come along. So thank you very much for your time and for your patience in listening to us. And I hope we'll see you in the task group.